On behalf of Villanova University and the College of Engineering, I'd like to welcome all of us to the Franklin Institute Awards Symposium honoring Richard J. Robbins. And the event this morning is co-sponsored by the Franklin Institute, and we're grateful for their support as well. I don't know if you're all aware of it, but there's another conference going on this morning on sustainability. It's next door. And I was just talking to a gentleman out there earlier today, and he asked me if this is where the boring symposium was being held. So I, of course, proceeded to tell him that engineering is not boring, and clearly he was not an engineer. And I have to be honest, last night at the dinner, that joke was stolen from me by Mitch, the head of the committee, but I wrote mine before he delivered his, so I think I have ownership of that. So for those who don't know me, I'm Jerry Jones. I'm the Associate Dean of Engineering. Part of my job is the undergraduate program. We have about 850 students, undergraduate students, in 5 different programs. We have about 200 graduate students in different programs, including master's and PhD. So it's about the size of us. And we've been doing engineering at Villanova for about 100 years, about 110 years right now. In all of our engineering programs, we strive to educate the whole-brained engineer. It's something that we think is very important. A whole-brain engineer is one who is not only able to handle the technical fundamentals in a sound way, which we strongly emphasize, but also possesses strong communication, ethics, and leadership skills. We think those are critical to being a good engineer, and they're crucial to successful execution of engineering projects, large and small. Many students take on leadership roles in their student professional societies like ASME and ASCE, but other ones do service trips to the U.S. and elsewhere, and these experiences serve to educate them about the different cultures, expanding their whole-brainness. For example, during each break period of the academic year, dozens of engineering students travel to Honduras, Kenya, the Philippines, Nicaragua, Thailand, and other locations to work on building structures or water distribution or electrical distribution networks. So with these thoughts in mind, I think that we can all see how appropriate it is for Villanova to be hosting this event today. Because when one looks at the Robbins tunnel boring machine, it's clear that only a whole-brained engineer could have produced this truly extraordinary piece of machinery. So again, I want to welcome everyone to the symposium this morning. If you have a few minutes later on today, I welcome you to take a tour around our campus. It's beginning to bloom this time of year. And I hope you have a very stimulating and enjoying symposium session. So I'll ask Fred Brecker, the sponsor for Mr. Robbins, to come up here and introduce the speakers. Enjoy the day. It's all yours.
Thank you, Professor Jones. Again, I'm Fred Brecker. I'm a structural engineer, graduate of MIT. I don't mind visiting this campus because we are brothers. I would like to welcome everybody to this event celebrating the medal that has been awarded to Mr. Richard Robbins for his development of the tunnel boring machine. First, I'd like to introduce Frederick Bartley from the Franklin Institute, who will give a few words of welcome.
Thank you very much. I'm very short, so I will come to the side. I'm Frederick Bartley. I'm the Vice President of the Center for Innovation in Science Learning and the Franklin Center at the Franklin Institute. I just want to give a few words about the awards program. 1824, Committee on Inventions in Philadelphia, part of the Franklin Institute, decided that they were going to recognize the best and brightest inventions, innovations, etc. 1834, that committee's name was changed to the Committee on Science and the Arts. They have been meeting continuously once a month since 1834 to decide globally who the best scientists and engineers, inventors are in the world. They've done a fantastic job, and today we're honoring, of course, Dick Robbins for the mechanical engineering piece. We have what we call clusters. We recognize medals in chemistry, electrical engineering, mechanical engineering, life sciences, earth sciences, and computer sciences. And we're 90 years older than the Nobel. And I say that because we have a rich history of doing this for almost 200 years. And what we do, unlike any other medal programs, is instead of just having that one day with rich pomp and circumstance where we pin a medal on the awardee's chest, while recognizing that they are the great scientist or engineer that they are, we think it's part of a bigger context of science education, engineering education for scientists, school children, etc. And so our awards program is actually part of an awards week. And we take this week to have symposiums such as this one and others throughout the local universities. And I just want to say on behalf of the Franklin Institute, I welcome you here. I welcome you again. Congratulate you, Mr. Robbins. And I hope you have a good symposium. Thank you very much.
Thank you. Thank you, Frederick. And now I'd like to start by introducing Mr. Robbins, Richard Robbins, who is the developer of the tunnel boring machine. He and his colleagues, Ms. Shani Wallace, who is the editor of Tunnel Talk, which is an international publication, Joe Roby, which is a vice president of the Robbins Company, and Mr. Locke Holm, who is the chairman of the board of Robbins Company, and the four of them will do their song and dance for the next 3 hours. Mr. Robbins.
Thank you. I'll just start by, first of all, thanking Professor Jerry Jones, your Associate Dean here, and we were expecting to have some students. Maybe we'll have a few join us. We decided that in all probability, most of the people here would be students. So you'll hear a presentation that's pretty fundamental that starts with, like, why tunnel? And what do you do with these tunnels, and what are the advantages of tunnels, and that sort of thing. So it's pretty fundamental for people who are engineers, and a lot of you didn't really need quite so much history, although we're very, very proud of the history of the Robbins Company and our development of these hard rock tunneling machines in particular. Now we're into hard rock and soft ground tunneling as well, so you'll hear something more about that. One of the things you will hear about is how we were the first at this and the first at that, and there's a lot of, we're very proud of our historical firsts and being in the leadership in the development of this science and this engineering. The other thing we did in order to produce this thing was this little lecture was to take some snippets out of our little videos and little animations that are marketing pieces. And so with the marketing things, you're going to end up being sold a tunneling machine by the Robbins Company instead of buying one from our competitors. So we apologize in advance for the commercial orientation of some of these things, but that's what we had to work with. So that's what we started with. I would also like to thank Fred Brecker for being my sponsor. Last night at a dinner, we learned what happened in their quest for deciding who would be given these medals. And I must say, it was really impressive, and I'm overwhelmed to have been chosen as one of the laureates in this auspicious organization. And there were quite a number of former laureates there at the dinner as well, so it was quite an affair. And I ended up with my little pin, which is a model of the medal that I will have given to me this evening. So with that as a background, we're going to do a little dog and pony show or tag team thing. Where 4 of us are going to speak this morning, and we're going to start on the early history of tunneling with Shani Wallace. And so Shani, if you can come up, and we'll the little deal is right up here, and I think it's on black screen. So if you just hit the little black deal there,
Hit that
you'll-
one
you'll-
and
you'll start.
we'll start. Okay.
Thank
Great.
you, Shani.
Thanks. Dick, thanks. Okay. Joe? Sorry, excuse me.
There it is.
There we have it. Okay. Great. Well, good morning, everyone. Thanks very much for having us here, and it really is an honor for me to be invited to join the team here this morning and present to you what I believe is a very interesting and fascinating story as we go through the development of what is today the modern tunnel boring machine, which is making possible tunnels that in the past were unthinkable. So, we'll begin right at the beginning, and that is the use of the underground space for tunneling to provide water and other facilities to the ancient civilizations, the Romans, the Egyptians. And you can see from the shape of the tunnel here, which is built in those days, they relied upon the inert strength of the rock itself, the shape of it to maintain its integrity. There's no support inside, it's hand excavated, and still stands today, many of them still in operation. The beauty of the tunnel boring machine is that tunnels are now excavated, built, and last for centuries in ground that would not allow such excavation, but for the fact that we have the facilities and the capabilities of modern tunneling techniques. The first attempt at excavating tunnels that were not hand dug was by the use of black powder, an invention that comes to us from the Chinese in the 19th century. Sorry, the 9th century, excuse me, bringing us right up to date too quickly. Here you can see that the black powder was first invented for uses other than peaceful civil engineering. Black powder was then used in the early tunnel excavations. The Hoosac Tunnel in the United States is one of the first long major tunnels that was built for a railway to go through the Hoosac Mountain, and between 1852 and 1873. It took an awful long time to excavate the tunnel, not all necessarily because of the difficult geology that was experienced at the West Tunnel, But other things interfered, including lack of funds, which hasn't changed to this day either. Many tunnels are still interrupted, delayed due to lack of funding. The black powder was inserted into holes in the rock face that were drilled with initially handheld drill rods, with the second team member whacking the end of the rod with a sledgehammer and the partner holding the drill steel and turning it for every impact. Pretty dangerous situation. The invention of dynamite increased the safety to a degree. It is still a very hazardous method of tunneling. And so one of the motivations for the invention of the mechanized tunneling systems was to increase safety and eliminate the hazards involved. Drill and blast then became one of the principal methods of excavating the early tunnels through hard rock. When it came to soft ground, there was no way really of separating the excavation from the support and the lining, which introduced the invention of Mark Brunel, who invented the tunneling shield. As you can see here, the shield was comprised of 12 sections in 3 levels, 12 across and 3 deep, with a man in every cell. So that's 36 men working at the face simultaneously. The boards here are supporting the soft ground ahead of them with these screw jacks. Take the screw jacks away, excavate a few inches, put the board back, and so work down this guy, this guy, this guy, and 12 across. Behind them, the teams that were building the layers of bricks and pushing the shield with the screw jack forward for every advance. Very slow, very laborious, very labor intensive, quite dangerous. Support really is the fundamental factor in a lot of the tunneling systems. If you can't support the hole behind you, the excavation is then a wasted effort. Here you can see the very early systems of supporting excavations with posts and wood beams. Oops, excuse me, we've gone too far. Wood was then replaced with stone masonry blocks that were quarried from the limestone and granite quarries. You can see the masonry lining on the bottom here. And also bricks. Yes, just those ordinary bricks that are building your homes. They are surprisingly very durable in an underground situation, and sewers that were built more than 150 years ago in London and other major cities around the world, as you can see, still in operation, still functioning perfectly well, under capacity, but still functioning in their original purpose. Brunel's tunnel was a square or a rectangular shape. And the next major development was the introduction of the great head circular shields. Again, with hand excavation of the face, but here with cast iron segments now instead of bricks or masonry for the support. And into the 1950s, the use of precast concrete segments to support the opening. Still again with hand excavation and wood timbers to support a soft face. We go then onto the early mechanical inventions. And some of these, you'll be surprised, were used very early on. This particular machine here was actually the beginning of the Hoosac Tunnel in the middle 1800s. The tunnel was, the machine was cutting a 24-foot diameter tunnel face. The Hoosac Tunnel is about 25,000 feet long, about 4.5 miles, and it was expected that this machine would advance at about 2 feet a day. With a machine at both ends, it was anticipated that the entire tunnel would be excavated in just over 1,000 days. Unfortunately, that didn't quite happen like that. And it took more than 25 years, in fact, to finish the excavation of the tunnel. This machine was built in Boston. It was taken to the east tunnel, the east face, the east portal of the tunnel, and was launched in a test pilot site. It excavated 12 feet and seized up in a boring round and stayed there for many, many years before it was retrieved. The hole it dug was used subsequently during the advance of the tunnel as a workshop. So nothing goes to waste. This particular machine, Cooke and Hunter were British engineers, and their idea was that you, with this trepanner type, gone too far again, was to have a pre-cutting technique. These machines would cut a slot around the full perimeter of the tunnel, and this particular machine with a second head on the inside and a drill steel in the center. And the idea was that once you had built excavated those slots, you would then blast the center out of each round, the powder being inserted into the center drill hole. Another idea from Cooke and Hunter was a rotating drum type machine, whereby the face is cut as the drum rotates this way, and the two side panels. So you can see you're building quite an odd-shaped tunnel, but the full face is being excavated as the machine moves forward. Colonel Beaumont was a colonel in the Royal Engineers in the British Army, and he invented early tunneling machines. This one here, a full-face rotating cutter head in the conical shape and excavating the material as the machine is pushed into the face. Many of these very early tunneling machine ideas were invented to satisfy the fascination of many tunneling engineers of the prospect of a fixed link between England and France underneath the Channel Tunnel, underneath the channel. So some of the very early ideas, as you can see, are pretty fanciful, but nevertheless, they were realistic. You needed to have the shafts to ventilate the 50-kilometer plus link, and underneath a drainage tunnel, just in case there might be a bit of water seeping through. John Fowler was, the record is quite vague on Mr. Fowler, but he invented this particular machine in 1881, and it is said that it was applied on an attempt at the Channel Tunnel, but the record is vague, so we're not quite sure, but it would be the first if it did actually happen. Beaumont's tunnel. This is also quite controversial. The industry does have its controversies every now and then, and this was controversial in the fact that Colonel Beaumont takes the credit for having excavated about 2 kilometers of an attempt at the Channel Tunnel in the 1880s. But a captain, Tom English, actually lays claim to that effort. This particular tunnel tunneling machine was powered by compressed air. The machine was, as I say, did excavate 2 kilometers, but for political reasons, it was stopped. It completed its near 2-kilometer length and then was stopped due to the political pressures. It was applied. And you can see here the log from that time, the advance rates, and you could say that the advance on average at just over 100 feet per week. Week? Yes, 100 feet per week was pretty good for those days. And you can see also that one of the reasons for some of the interruptions was due to the fact that visitors were coming down to take a look. That hasn't changed either. The fascination for the visitors to go down into tunnels remains today. And as a visitor to many of the tunnels around the world, I can vouch for the fact that they get a little peeved if the routine of the effort gets interrupted because visitors need to be taken into the heading. So the reason the Channel Tunnel effort was stopped was because there was the fear of invasion from the French, and that didn't change either. Even up until the successful attempt in the late 1990s, there was still in some quarters a fear that the tunnel, the fixed link, would be abused and used for the wrong reasons. This here, we'd have to say, in that case, is that France is here and the infantry are marching through to England over here. Beaumont's machine, even though it was stopped as an early attempt at the Channel Tunnel, did actually go on and be used very successfully in 1884 for one of the first fixed links underneath the Mersey River in Liverpool, between Liverpool and Birkenhead. They're wearing wet slickers, so you can see that it wasn't dry down there. Back to the Channel Tunnel, another effort in the early 1900s, the 1920s, and the Whitaker Machine. You can see that we're getting more elaborate with the setup, but principally the same applies. Mechanical methods of excavating the full face. From there, we move on and we bring ourselves to the middle of the 20th century, and I pass over to Dick to take us through that part of the story. Thank you.
Thank you.
Cheers.
Well, I get to talk about the first modern tunneling machine. As you can see from Shaney's slides, there were quite a number of mechanical tunneling machines, one of which, Colonel Beaumont's machine, actually completed a commercial tunnel under the Mersey River and would have bored the Channel Tunnel successfully. They actually bored a couple of kilometers on the French side as well, which Barbara Stack didn't have covered very well in her book. But a lot of those pictures of those old machines were patent drawings taken out of the patent files. So when my father, Jim Robbins, invented tunneling machines, he thought he was the first to come up with the concept of a mechanical machine to drill tunnels. Later on in his life, in fact, the year before he died, in 1958, in 57, he went to the French side and was consulting with them about the Channel Tunnel, and they had pumped out the French tunnels that were built 100 years before in the mid-80s, 1880s, and he went down the tunnel and went into the tunnel. They pumped it out again when I went back in 1974, when we built a machine for another attempt at the Channel Tunnel, which didn't succeed. And they pumped the tunnel out, and I was able to go in the old Beaumont tunnel, and we picked up a few little pieces of scrap metal which we think were worn out cutter tips and things like that in the tunnel. And we could have kept going, but the floor of the tunnel had heaved so much that you had to crawl to get through the hole. So anyway, that's a side line. Let me just go forward. This is a picture of Jim Robbins, the modern inventor of tunneling machines. He was a mining engineer. He raised us in Alaska, where he operated placer gold mining operation. The mine eventually went broke. We left Alaska and moved in with my grandmother and her home in just north of Chicago, and we lived there while my dad was a consulting engineer for some coal mine operations in central and southern Illinois. And it was there that he invented this coal boring machine, but actually this was a carry-on from an earlier British twin-head coal machine, and all he did was make a new modern one with modern mechanical features, gearing, electric motors that were flame-proof, and hydraulics, and made the thing work. Interesting point was that this machine had some disc cutters here on the rotating cutter head, and these arms had drag picks tipped with tungsten carbide. So the machine actually cut tunnel face with the drag picks, and then the disc cutters rolled along in between and broke the coal. At that point, the railroads wanted chunks of coal. They didn't want fine coal, and so that was an attempt to keep the coal coarse. The Goodman Company, Dad, in order to recover from his debts, sold his development to the Goodman Company, who made a whole series of these machines, which were later used not only for coal mining, but also for salt and potash mines. So what happened was that Goodman also made like a chainsaw, a big chainsaw that was, I think there were about 8-foot long bars that would cut coal. And they would cut the top and the bottom of the coal seam in order to break it out. And a contractor on the Fort Randall tunnel, this is on the Missouri River, a major earth-filled dam. These tunnels had to be used for power and diversion tunnels. Had used a Goodman coal saw to cut the periphery of the tunnel, and then they drilled the center and blasted it. And the advantage here was that they saved about, I think it was about 3.5 or 4 feet of overbreak when you blast the whole tunnel. This very weak rock, a shale, would have to be filled with concrete, and they saved that like 4 feet of thick concrete by cutting the outside. So this is a picture here of of the coal saw periphery, and they blasted the center. And there's a machine mounted on what we called a jumbo. So the next the next dam was the Oahe Dam in South Dakota, also on the Missouri River. Needed the same kind of tunnels. And the contractor, who was a low bidder, bid it with this device. And he came to Goodman and said, well, I want you to build me another one of those jumbos with a coal saw. And they said, well, we don't design that kind of equipment. Jim Robbins he's a consultant to us now, and he'll be happy to design one for you and build it. And Dad convinced this contractor, F.K. Mitri, to let him make a machine that would just cut the whole face, and you forget about the blasting. So he built this machine, built it in Chicago at the Chicago Bridge and Iron Company. The inner cutter head here turned in this direction, and the outer cutter head turned in that direction. Whoops. I guess I hit the wrong button. There we go. Anyway, that was an attempt to balance the torque required for these cutters to bore the face. As it turned out, the machine was so heavy, you really didn't need to react to torque that way, but it was very useful because the ground was very weak and a soft rock and fractured, and it would cave in. And so the central part of the cutter head was often held still while the outer part was used and to pick up the cut rock and send it out on a conveyor. This is the machine being withdrawn with the outer portion taken off, and you can see that the tunnel is lined and with rebar and everything ready to pour concrete for the tunnel lining. Then my dad, on his second, third, and fourth machines, decided he could cut harder and harder rock, and he built this machine for a job in Pittsburgh, a sewer tunnel that went under the I'm not sure which river. I think it was the Ohio River. Anyway, I worked on this job in my vacation periods from high school, and my job was to be at the conveyor at the back end of the machine and count the number of broken cutter bits as they came off the conveyor, so that when they got too many of them, we'd stop and change cutters. This machine used, well, let me back up again. It used, I keep hitting the wrong button, disc cutters, double disc cutters, and drag picks. And these drag picks were like a machine tool with tungsten carbide on the tip. But the rock they were boring had layers of limestone and shale, and the shock was great enough so that it would just break the cutters. This was a gripper shoe that fit on this position here. That's Jim Robbins standing in front of the machine as they were withdrawing it from the tunnel. I think in this particular case, forever. Most of the contractors use these machines for up to the point where the owner of the construction company would come in and take a look and say, one of them, a guy from Chicago where he built one of these machines, said to the foreman, our guy, how long would it take you to get that machine out of the tunnel? And he was told, well, we can do it in about 2 weeks, take it all apart. He says, you've got 2 days. So that's a picture of the tunnel face. Dad called his business James S. Robbins and Associates, which is a name we used for until the mid-60s when I changed the name to the Robbins Company. but, and it wasn't a corporation at that point. You can see the drag pick grooves and the marks in between where the disc cutters broke the rock. This was one of his patents and an invention that when I did a lecture in Moscow, they presented me with a Russian textbook on tunneling, and it had Dad's patents in their book. Then the most important breakthrough, and this is really what enabled hard rock tunneling. This is the Humber River Sewer Tunnel up near Toronto. In 1956, he realized that these drag picks weren't going to work in hard rock. And so he arranged the cutters in such a way he could use them and try to cut the rock with them, and then take them off and see if the disc cutters by themselves would cut the rock. And it did. They succeeded. This is a picture of the machine with, you can see the gripper shoes here. The machine was skidded on this shoe to support the front end. It had side stabilizers to stabilize the machine, and a lot of the features that our current machines today have, although, oh, I hit the wrong button again. Let me go back. This, there. This gripper was rigidly connected to the machine. So when you grip, you've got to go straight ahead, and that's all you can do. So if you want to turn the machine, you have to adjust the position of the machine, grip again, and then go forward. So the next machine he built was this 29.5-foot diameter machine, also for the Oahe Dam. This was the third machine that was used there. This was in 1958, and this machine was about half built. I had joined him, my dad, 3 months before, and he was killed in a plane crash at that point. So that was the end of the era of Jim Robbins. It's a real shame because we were really making progress while he was alive. He was a great inventor. But we finished the machine. This is the same thing, but one cutter head now instead of the double cutter heads. Shoving here with jacks pushing against the steel ribs in the tunnel, and the torque reaction supported by the mass of this jumbo. So I'm going to move a little more quickly now. It turned out that was our 6th tunneling machine. We went for about a year and a half. We made the machine work, and then I gradually laid off all our workers, and it was just Dad's assistant, who happened to be the bookkeeper and office manager, and myself, the two of us, for quite a period of time until we got another job. But in the meantime, there were a bunch of other companies that saw that you could make tunneling machines work. This was DMAG Company, a big German company, made this machine. Oh, sorry, hit the button again. This was in 1963, so it was only 5 years after my dad died that they built this. The Russians actually, this was published in the Glukov magazine in 1961, so they did this in 60, only a couple of years after Dad died. These machines were using rolling cutters, gear type teeth, and none of them really could progress in hard rock. This is another machine that used that type of cutters, the Lawrence Machine Works, which became part of Ingersoll Rand, used this machine with a tricone or 4-cone bit to make a probe hole, expand the bit in front, and then pull the machine forward. The problem was that if the ground was broken, it would just pull the face to you. And so it also had grippers at the back here to grip and shove the machine forward. This was the first shielded tunneling machine. Komatsu company, who make the bulldozers in Japan, became a licensee of ours in 1962. And this was the first time that a hard rock tunneling machine, oh, hit the wrong button again. There we are. This machine would bore a full size, and then when they got into a fault, they would assemble this shield around the outside of the machine and shove it through the fault zone with the machine just cutting the inside. That didn't work very well either, because they have faults that have a lot of hard rock that have to be cut with the periphery. The Jarva company was our first major competitor in the United States. They were operating in early 60s. It's a contractor that built machines for himself. This machine had well, I keep hitting the wrong button, I'm sorry. These grippers were 2 sets of cruciform grippers, and the machine would go in straight lines. So if you wanted to steer the tunnel, you'd make a new adjustment to the angle of the machine. This was a much more recent version of the machine, also using these cone-type multi-carbide cutters on the cutter head. Their most recent machine had horizontal grippers and also single disc cutters. So this machine looks very much like a modern tunneling machine. Ingersoll Rand Company acquired the Jarva company, and Atlas Copco Company, and Atlas used this basic design of machine for many, many tunneling machines for very hard rock. This is a machine which was developed in Switzerland for undercutting the rock, and with drag picks, with tungsten carbide. And they claimed that if they used these properly supported, it could cut very, very hard rock. So this is a picture showing how those drag picks would undercut the rock and break it back toward the machine. They did bore some very hard rock with this technique. So Atlas Copco acquired the Whitaker development and made machines using a single full width cutter head that goes up and down, and this was called the mini full facer. Here's a machine breaking through a tunnel in a mine in Sweden. So the next section of this talk is going to be Lacombe is going to speak on the different types of modern tunneling machines.
What we call modern tunneling machines, we really break them into 3 categories. We've got rock machines that are just designed to bore rock, and that takes different types of machines. And there's lots of tunnels that part of the tunnel will be rock and part of the tunnel will be soil. you can imagine that as you drive, even in Philadelphia here, you drive down the road, you see rock, you see soil, and they want a straight line tunnel, so a lot of the tunnels are mixed, part rock and part soil. And then of course there's tunnels that just are in soil and soft grounds, in the big deltas, in London's, all London clay, no rock under London. A lot of tunnels that are built in Shanghai now, a big delta city. There's no rock in these deltas, it's all soil under the water table. And so that requires a whole different type of machine. And I'll just go through the rock and mixed ground machines here, going the wrong way. And we even take and break down these hard rock machines into special categories too. We have what we call an open machine. In that case, we're assuming that the rock itself is strong enough, like those bricks, to self-support itself, and that takes a special type of machine. And then we have shielded machines. So we go to these open machines. The first one Dick proposed, those ones that we were looking at there, they were mostly open machines. We did see some shielded machines. And the first one that really worked to some degree was built in 1952. Then really the next invention was this pressurized bulkhead machine built in '62 that Dick designed for this very tough job in Paris. And when we were coming in the car this morning, we were talking about this tunnel, and this tunnel was rather unique because it was under pressure. They were trying to hold the water table, but they ran into this coal seam, and because they had so much coal and pressure, the tunnel actually caught in fire. The coal caught in fire and was burning while they were trying to excavate this tunnel, and they had to flood the tunnel to put out the fire to start the machine again. And there's been lots of horror stories about tunneling, and I'll rather move on to better times. The slurry machine was first invented by the Germans. That they used, just like you know about slurry, they pumped it in and held the pressure by a pumping system. And earth pressure balance, which you'll see along here, this is kind of unique, and that was invented by the Japanese. And the double shield was again a Robbins invention. And now around the world you see us all, there's about 4 or 5 main competitors, and we kind of fell into these categories of machines, rock machines and slurry machines and shielded machines and earth pressure balance, and we're all using each other's technology. It's like an amalgamation of technologies. Again, as you break these things down, they're used for the different rock types or different ground conditions. A lot of the tunneling now is kind of forced on us by the cities there. They need a subway, and hey, you can't select the geology, so you have to make the machine adapt to the type of soil it is. So we're a lot of times just boring under the city, and there's the big buildings above you, and so you can't have any ground subsidence, so you got to hold the water pressure, you got to keep everything just as is condition, only put the tunnel in. So we look at this in a modern tunneling machine. This happens to be built by us and assembled in China. And rather than explain how these things work, this video does it in this little clip will do it in a much better way.
Robbins TBMs range in diameter from 3 to over 14 meters. The front of the tunnel boring machine consists of a rotating cutter head in which disc cutters are mounted. The cutter head is supported by a main bearing. Robbins main bearings have the largest bearing to tunnel diameter ratio in the industry. This results in superior bearing life when cutting hard rock. The cutter head holds disc cutters, which consist of a shaft, bearings, seals, and a rolling hub. The disc cutters are not powered directly. As the cutter head turns, the disc cutters roll when they make contact with the rock face. The cutters roll in concentric circles. As the force on the cutter head increases, the rock beneath each cutter is crushed and fractured. Eventually, these fractures meet, and rock chips or muck break away from the tunnel face. This process is known as curve cutting. Buckets in the rotating cutter head scoop up muck from the bottom of the tunnel. As the cutter head rotates, Gravity pulls the muck from the buckets and deposits the excavated material onto a belt conveyor inside the main beam. The muck is then transferred to the rear of the machine for removal from the tunnel. Eventually, the disc cutters wear out. Cutters can be replaced from the front or the back of the cutter head. The Robbins TBM offers unique cutter head efficiency. Hard rock cutter heads can vibrate intensely during operation. The Robbins TBM provides hydraulic bracing which expands radially to significantly reduce vibration and disc cutter wear. In addition, Robbins hard rock cutter heads are significantly deeper than the industry standard, further enhancing the rigidity of the structure and rock cutting efficiency. The force which thrusts the cutter head into the rock face is provided by multiple propel cylinders which are mounted to gripper shoes. The gripper shoes are firmly anchored in place by gripper cylinders, which push the shoes outward against the tunnel wall with tremendous force. The gripper shoes provide the reaction space for the propel cylinders. A TBM boring stroke is completed when the propel cylinders are fully extended. At this point, the TBM must be re-gripped. To do so, the cutter heads must stop rotating. Then, rear legs are lowered to support the machine's weight so that the gripper shoes can be retracted from the tunnel wall and pulled inward. The propel cylinders are then retracted, which advances the gripper carriers and shoes. The gripper cylinders extend the shoes outward, once again anchoring them against the tunnel wall. Finally, the rear legs are retracted and boring can resume. The floating gripper system created by Robbins using a sliding trunnion mount allows the TBM to be continuously steered while boring. This superior system allows for precision steering adjustments and results in a more accurate alignment and a smoother tunnel face. Proper support of the rock as the TBM advances is critical to the safe construction of a tunnel heading. Robbins provides a variety of mechanized devices to assist in rapid, comprehensive ground support. Rock bolting is quickly and safely achieved by the use of Robbins custom-designed drill fixtures. Drilling takes place primarily under the protective canopy of the shield fingers, supported by previously installed bolts. A wire mesh erector provides for quick placement of large panels of welded wire fabric. A ring beam erector assembles, correctly positions, and expands a multi-piece ring beam, all within the protection of the shield finger. In some cases, remotely controlled shotcrete robots are the best solution for ground support in fault zones or highly fractured rock. These robots facilitate the controlled and rapid application of shotcrete at a minimum of time and cost. Probe drilling can detect the ground conditions ahead of the TBM, such as fault zones or water. Probe drilling is typically performed at distances of 30 to 60 meters ahead of the machine. If weak ground is found, it can be pre-crowded to increase.
That's it. So I think that explains how these machines work better than I could even come close to explaining it. And of course, it looks easy in the animation, but it's much more exciting to see them doing it underground, really physically doing it, and the rock pouring in on you, and or the water pouring in on you, rock falling down, and these guys working there. It's always an exciting adventure to go underground. Another invention that Dick did was make a combination of these hard rock machines. You can see the cutter head here is a big, tough cutter head, and the machine's completely shielded. And what they do here is they bore and set the line simultaneously, and this animation will show it. This is only about 3 years old in a project we're doing down in India, boring a 42-kilometer tunnel, 10 meters in diameter, under a Tiger Park there. So there was no intermediate access, one machine on one end and one machine on the other end. And amazingly, the machine today goes as we predicted. That's a big step forward in our business.
Double shield TBMs consist of the rotating cutter head followed by an arrangement of shields, a forward shield, a gripper shield, and a tail shield. A smaller diameter telescopic shield attached to the rear shield slides within a larger diameter telescopic shield attached to the rear shield. These shields offer protection from falling rock. In normal or double shield mode, gripper cylinders push the gripper shoes onto the tunnel wall to react to boring phases. The gripper shoes provide the reaction base for multiple propelled cylinders, which then extend to push the cutter head support and cutter head forward. As the machine advances, the telescopic shield is exposed, providing protection from the surrounding tunnel environment. The gripper shield remains stationary during boring. A segment erector is fixed to the gripper shield, allowing precast concrete tunnel lining segments to be erected while the machine is boring. The segments are erected for the safety of the tail shield. It is the double shield's ability to erect the tunnel lining simultaneously with boring that allows it to achieve such high performance rates. The completely enclosed shielded design also provides a safe working environment. If the ground becomes too weak to support the gripper shoe pressure, the machine thrust must be reacted another way. In this situation, the machine can be operated in single shield mode, the same method of operation as Robbins single shield TBMs use. Auxiliary thrust cylinders are located in the gripper shield. In single shield mode, the thrust cylinders transfer the thrust from the gripper shield to the tunnel lining. Since the thrust is transferred to the tunnel lining, it is not possible to erect the lining simultaneously while boring. In the single shield mode, tunnel boring and tunnel lining erection are sequential operations. Proper support of the rock as the TBM advances is critical to the safe construction of a tunnel heading. In addition to the tunnel lining, there are multiple options for additional ground support. Probe drilling can detect the ground conditions ahead of the TBM, such as fault zones or water. Probe drilling is typically performed at distances of 30 to 60 meters ahead of the machine. If weak ground is found, it can be pre-grouted to increase ground stability.
And the key to this, in those earlier machines Dick was showing you, they showed you all kinds of big cutters and tungsten carbide cutters, and these, you know, when we tell people, okay, we cut this very hard granite and it's or quartzites, they always ask, well, what type of material do you use to cut that rock with? And the answer is just simple chisel steel, the type that you would use to chisel with, but it's a little more exotic. And the cutting is just this real high exotic or tool steel, special treated tool steel, and then we just under high loads it just wears down. This tip wears down, and then when it wears down to this, we remove this whole section and put on a new disc. And in hard rock, we usually use about 10 or 15 discs before we wear out this bearing assembly. And this has been the key in the success for tunnel boring. And even in very hard granites at about 15 feet diameter, the hardest granites you'll find, we can still get 4 or 5 feet an hour, and much higher rates in softer rocks. And so this is the tool that really cuts the rock. And today we have them in sizes up to 20-inch in diameter, and the techniques of putting them on are very fast and very safe. And that's the key to it right there, the disc cutter. It's just an assembly. One last, I think then.
You have to go back, I think, and forward again, then we'll start.
One, bang, bang. One more shot on how this works. And this is a close-up shot, actually done in the lab, how this disc cutter works. You can see it cuts just this groove, and the chips start falling out, and that's what they just break out like that. That's a big chunk of granite being cut by a cutter in a lab. You can just see how the rock actually explodes, and that's what's going on all the time when we're cutting. And it's really a kind of an exciting process. And you can also see how this thing jumps around. The camera's not moving here. I guess it would be if you were in the cutting head, but this is actually in a lab. And what's interesting is you see how that thing's jumping back and forth. And this cutting tool is very, very stable. And what we had to learn is how to make these machines unbelievably robust to withstand these forces. So the cutter heads that we have today are just tremendously heavy pieces of material, and just to react those forces that you see jumping up and down there. So my little stint is over here. I'm going to ask my partner Joe to go on with the software machines.
Soft ground machines are a bit different from the hard rock, and you were just witnessing the violent mechanisms involved with disc cutters and excavating rock. And soft ground is the problem is kind of the opposite. In hard rock, it's getting the rock to come down is the problem. In soft ground, it's getting it to stay up, to not over excavate. In soft ground, the ground, of course, tends to flow right into the tunnel, and of course, in urban areas, it causes subsidence and can cause catastrophe, buildings falling, railroads sinking, and so the key is trying to match the volume of material excavated with the advance rate of the machine, so you're excavating exactly the correct volume of material. And this gets further complicated when you're working under the water table. Then of course you're trying to control the volume, you're trying to also control the pressure in front of the machine, and then we have kind of two different solutions. And one is with earth pressure balance machines, which have screw conveyors, and they excavate the material controlled volume. And when there's sufficient fine material like clay, you can actually form a watertight plug within the screw conveyor, which keeps the water in front of the machine, and out of the back of the screw conveyor comes primarily solids. When you get into porous ground and sands and gravels, that you can no longer form this watertight plug within a screw conveyor, and the water would just pass right through these coarse materials into the tunnel. And there we use slurry machines. And so this bit of the talk is just covering those soft ground machine types. They say there's two fundamental types: earth pressure balance, which were created by the Japanese, and slurry shields, which I think were more or less simultaneous, kind of German and Japanese inventions, and they've been modified substantially since those first machines. This is an example of an earth pressure balance machine, which is also expected to encounter some large boulders or harder rock, which is why this machine is actually fitted with typical hard rock disc cutters, as well as ripper teeth or other type of cutting devices. Again, we have a video which will show much better than I
Robbins
can.
earth pressure balance machines range in diameter from 3 to over 14 meters. The front of the tunnel boring machine consists of a rotating cutter head in which cutting tools are mounted. The cutter head is supported by a Robbins main bearing, which has the largest bearing to tunnel diameter ratio in the industry, resulting in superior bearing life. For soft ground excavation, the back-loading cutter head can hold a variety of carbide cutting tools. In mixed ground conditions containing sections of hard rock or boulders, the cutter head is fitted with a combination of carbide tools and single or double disc cutters. As the cutter head turns, the cutting tools make contact with the material to be excavated, known as the face. A unique smooth flow spoke type cutter head design draws more muck from the face with a large opening ratio, resulting in decreased torque and thrust requirements and less abrasive wear on the cutter head structure. Depending on the ground conditions, additives can be injected into the face through multiple points on the cutter head. With additives, the face of the tunnel is more stable and is less likely to collapse during excavation. The additive may consist of foam, polymer, or bentonite. During the excavation process, ground material or muck moves through the cutter head to a mixing chamber. Inside of the chamber, the muck is pressurized and holds the tunnel face. The pressure differential between the chamber and the screw conveyor then draws the muck into the screw conveyor. As this happens, the muck's pressure is reduced from ground pressure to atmospheric pressure. The depth of the tunnel, the ground material, and the water level above the tunnel determine the ground pressure. In the case of lower ground pressure, only one screw conveyor may be needed. For projects with high ground pressure, Robbins installs 2 screw conveyors in order to bring down the pressure smoothly. After passing through the screw conveyors, the muck can be transferred to an open belt conveyor and then removed from the tunnel by muck cars or a conveyor system. The ability to balance the earth pressure is essential in order to safely and efficiently excavate the tunnel face. A TBM operator can control the pressure in the chamber continuously. To raise pressure, the operator can either increase the machine's rate of advance or decrease the rotation of the screw conveyor. To lower pressure, the operator does the opposite. either decrease the rate of advance or increase the rotation of the screw conveyor. The EPB cutter head is followed by a shield body. The shield body may be divided into a front and rear section for when the machine requires articulation during curved tunnel drives. During an EPB boring stroke, the cutter head turns and thrust cylinders extend to push the machine forward. These cylinders transfer the thrust to the cutter head by reacting against the tunnel lining. After each TBM advance, the thrust cylinders retract. Then, another ring of segments is placed by a segment erector, and a new boring stroke begins. Since the cylinders react against the tunnel lining, it is not possible to erect the lining simultaneously while boring. Thus, tunnel boring and tunnel lining erection are sequential operations. Using a process called active articulation, Robbins EPBs can produce tight curves with a radius as small as 3 to 4 times the tunnel diameter. Active articulation allows the thrust to be transferred equally to the entire circumference of the segment ring, eliminating the problem of ring deformation. The articulation occurs between the front section and rear section, which are connected by articulation cylinders. Other EPBs use a process called passive articulation, which places uneven pressure on the rings while steering and causes deformation of segment rings. Proper support of the tunnel walls as the TBM advances is critical to the safe construction of a tunnel heading. As the machine bores, temporary gaps form naturally between the soft ground and the tunnel lining. The boring process also creates a risk of settlement and upheaval at the surface. To stabilize the soil and fill gaps, the process of backfilling is used. Robbins' backfilling system utilizes 2 liquids rather than the industry standard 1 liquid to achieve more precise and effective backfilling. The liquids by themselves remain fairly viscous and are combined together in the tail shield where the hardening process begins. The liquid is injected from several points of the machine and flows around the tunnel walls, filling in any gaps and hardening rapidly. The entire process utilizes low-pressure pumps as opposed to concrete pumps, minimizing the risk of ground disturbances.
So that's earth pressure balance machines. This is another earth pressure balance machine cutter head. This one is intended straight for soft ground. You won't, there's no rolling disc cutters on this. It tends to be used where you see primarily clay or possibly clay and sand material. There's a large center spade to keep the material moving out from the center. Otherwise, the slowest part of the head, it tends to collect there and cause high pressures and a lot of wear on the cutter head itself. And again, this is a earth pressure balance machine cutter head, which is also expected to cut mixed ground, including boulders or some hard rock sections. This one, in fact, is working now in Guangzhou, China, 2 machines of this type for a metro system there. Then we'll move on to slurry shields. Slurry shields have use only water or water with bentonite and other additives to carry the soil out and to also maintain the pressure on the face. These are 2 large diameter slurry shields manufactured by Mitsubishi, a company with which we have a close relationship. The typical slurry shield is a simple shield, much like an EPB, cutter head, single shield, and a segment erector with a concrete lining and a backfill injection system for filling behind the segments. The fluids are injected into the front of the machine, and the entire area from the pressure bulkhead behind the cutter head to the face is all kept pressurized with this liquid. Typically the slurry coming out of the machine is carrying about 10% solids by volume. Those solids are then separated from the water up on the surface using various methods. I won't go into the detail of that. It takes quite a lot of equipment of different type to separate that material, and then returns back the water to the machine. There are different designs which use simply fluids to maintain the pressure there. There are also some designs which use an air bubble as a sort of accumulator to maintain the pressure on the face of the machine. When you're cutting very fine materials, clays and so forth, it takes quite a lot of technology to separate material from the liquids at the surface, and you have to remove nearly all of it, or an accumulation starts, and you can quickly get to at the 10% level of solids and just fine material, and the machines will start to stop excavating, essentially. So these machines work in permeable ground underwater, under the water table, where no other type of machine can work. With the proper design, the fluid pressure can be precisely controlled to prevent settlement. The disadvantages are that the separation costs can be quite expensive, and some of the materials are not so environmentally friendly that help you to separate. If you get extremely permeable and drier ground, you can lose slurry and lose the ability to excavate. Blowouts to the surface, if the pressures aren't controlled precisely, can be a problem. This has happened on a couple of jobs when they were operating close to the bottom of, say, rivers. And access to the face of the tunnel boring machine for maintenance is a major problem. Of course, when you're working in some certain conditions, you can't evacuate the face. In other conditions, you can inject polymers or bentonite into the face and form what they call a filter cake, and then remove the water and keep air pressure. Then you can send workers in under air pressure to maintain the machines. But in certain geological types, it's impossible to form that filter cake, and therefore to evacuate the chamber, and it becomes essentially impossible then to do maintenance on the machines. Here are some rather unique Japanese developments. This is actually one machine. It looks like two faces, which ends up resulting in this sort of binocular cut, which was used to excavate a station on a subway system. The Japanese have made a lot of very unique slurry machines and earth pressure balance machines for excavating various special underground civil engineering construction projects in Japan. I think we'll stop here for a short break and come back and finish this up in about 15 minutes.